Okay. So welcome for today's live session. This is week 3 live session, the third live session for this economic operations and control of power system. And first of all, just I would like to ask whether the way we are going through these live sessions is this benefiting you? Do you want any changes, any suggestions for the live sessions?
No, perfectly all right, sir.
Okay. Okay, good. These are a reminder for assignment 3 and 4. The deadline is tomorrow for assignment 3rd, and for 4th it is 21st. I hope the recordings are also available. You're able to
Yes, sir.
access them.
Yes, sir. Yes, sir.
Okay. The link you can find in PDF of the uploaded presentation as well as on the portal. The Google Drive link is also available. We will begin with the week 3 overview. Week 3, we discussed the first week. Week 1 was an introduction. Introduction, preliminaries are introduction to the course and different generation technology, optimization preliminaries. And then week 2 was on economic dispatch. Plus also on dynamic programming. The dynamic programming concept which we have learned in this week 2, that will be used to solve the unit commitment problem in week 4. I think you would have watched some videos that we will discuss. So today is on week 3. There's also a recap of most of the concepts, which especially these power flow concepts, which we already study in undergrad. AC and DC power flow. The load flow and power flow, these two words are used interchangeably, but power flow is a better correct word, we would say, instead of load, because load doesn't flow. It is the power which is transmitted, or it power flows. So power flow is it's the correct term, correct usage. Okay, so we discussed this power flow problem. First of all, the DC power flow, and then also AC power fluid solution methods, which we already know, like Newton-Raphson, starting with Gauss-Seidel. Gauss-Seidel is the most basic one, then Newton-Raphson, then decoupled power flow, fast decoupled power flow. And in between these two, there is one more quasi-Newton. Quasi-Newton, or which has been termed as dishonest NR in the slides, in the lectures. There's then last one was this transmission losses. How to calculate these transmission losses. Most of these things which we are studying, equations we use DC power flow equations as well as AC power flow equations. But the methods which we have studied, like this lambda iteration method for economic dispatch, or uh, the same lambda iteration method with and without losses, we have seen for economic dispatch. with losses. So this will include that penalty factor. Instead of using these, now we directly write the equations in the solver, and because earlier the computation was a challenge when these methods were developed, these lambda iteration techniques and all these dynamic programming even, they were developed when at the time when there was computers were not there or analog computers were there. Computation was a challenge, but now we have very fast processors, supercomputers also. So we have good solvers also. Like, can you name some solvers? Which optimization problem solvers, commercial solvers, or even open source? They're not audible. Are you saying something? Can't hear. Uh, yes, so I was asking solvers. Do you know any solvers?
No idea, sir.
Okay, no problem. We'll just tell you. So instead of using these lambda iteration methods, now we directly use the solvers. We write these equations, and we have different even softwares for that also. The way we write equations, such as the simplest our economic dispatch case, which is to minimize f of x and subject to some one is power balance equality constraint. It's a summation of generation is equals to load, and then the generation should be between minimum and maximum, PG max and PG min. This is a very simple problem, and now this fx can be linear also. We have discussed linearized piecewise linear cost curves. You can convert the quadratic function into piecewise linear, then it will become complete linear program. It will be an LP. If we use quadratic cost function, the original, then it will become a QP. Okay, so if we simply write this, so C transpose X, which is Fx cost into X is here PG. You can write PG only. Subject to same constraint. We can write these constraints in the same way. The way I'm writing this, that summation of PG should be equal to PL. So this can be written in one line in in Python, Julia, MATLAB. You can write it. So these are the platforms which provide us the way to write these equations, and there are generally two methods, and some of the solvers, I would say, solvers are also, there are some open source solvers, and there are many commercial solvers also. And the list of these solvers you can easily find if you you heard of GAMS?
No,
GAMS,
sir.
have you heard? So this is general algebraic modeling system. So it's a language. It's a platform which provides us a way to write these languages, these equations, mathematical equations. It's a language to write these mathematical equations, big equations we can write using this. Another is AMPL. This is also another language. I do not remember this. I think algebraic mathematical programming language something. I don't remember. But this is also a mathematical programming language. This also is another language. All both of these are commercial. These are not open source. Then these are the languages used to write these models, but they cannot solve them. They will simply help us to easily write these equations in these form. So this sum summation we can use some word maybe is there. So sum can be used to write this PG. So PG something we can write and this will be equal to PL. In this way, in a single line, we can write this. Similarly, there are different ways. So these are the two popular languages which are commercial. And then they need some solvers which can solve these system of equations. One is commercial is Gurobi is one solver. It can solve LP, QP, MI, QP, MI, QP. Then Mosaic is there. There are a lot of solvers, and when you see, if you go to GAMS site, you will find all the names of all the solvers. Even one online solver is Neos. This is an online solver. You can upload your file and then it will give you result on your mail ID. There are some open source solver like CBC, Higgs. Another language here you can write it is CVX is also one language. It is developed by Stanford University, Professor Boyd. CVX. These are different in MATLAB also we can write. MATLAB provides, so there were some, uh, if you want to write this economic dispatch or unit commitment problem, which we are discussing in this course or another optimization problems, which we'll be discussing in the future weeks, you can write these optimization problems in MATLAB and get your results. You can easily verify them. It's very easy. And there are two ways in MATLAB you can do it. One is problem-based solver and one is problem-based and one is solver-based approach. I think for this course also in the course description there is one link available for a MATLAB course. Have you seen that? MATLAB on-ramp?
Sir,
In the, I think, description of this course there is one link for a MATLAB optimization on-ramp course.
yes, sir, yes, sir.
Have you gone through that course?
No, sir, no.
Okay, so if you're interested to in writing these simple equation, and easily just by solving them, you can easily get all the output. If you want to learn that, this course is the most basic, and it will help you to understand this problem-based approach of MATLAB. The solver-based is different. For each of the solver, let's say you want to write LP, this is a linear program. If you want to write QP, or if you're writing any generic code, then genetic algorithm. These are the functions available in MATLAB. So if you write LP program, it will be solved by LP. linprog is there. Linprog function is there. For integer programming, int linprog is there. And quadprog for quadratic programming. They require set of matrices and vectors. If I am writing the C transpose X subject to AX is equals to B. It can be even Cx less than equals to D. Then you need to provide the C, A, B, C, and D. A is a matrix here. It's not C. Call it G. And G is also a matrix here. B and D are vectors. All this information we need to provide in this function. So for that we need to create A, B, C, D matrices and vectors. And if the problem is very small, we can do that manually. But if problem size is very large, writing these matrices is a very it's error prone. It is likely to be it's more likely to have error because while dealing with big matrices, it becomes very difficult. Some one zero or minus one here and there, and everything your answer will change. So that is very problematic. That's why this problem-based approach is used, and that you can learn if you are interested. It will surely help you. You can. It's when we write these small codes and we see the answer. If you want to see how things change by making a small change, if I change the load or if I add one more constraint, how things will change. We can easily visualize and analyze the answer because we cannot do it manually all the time. All these programs, even quadratic program, we cannot solve manually. But if you want to see how things change by changing the load, how the generation is changing, how the generation is getting distributed among all the generators, so everything we can easily do right by writing this code. Only once the code is written, we just have to change the load or small changes we can make and easily see the result. It's a very handy tool. So if you're interested, you can learn these things. And there are many solvers. Even in MATLAB, we can use CVX. You can use YALMIP is another programming language which can be used in MATLAB because if we write big programs in MATLAB, MATLAB becomes very slow because once you use for loop in MATLAB, it becomes very slow. C, C++, even Julia, if you write for loops, then you can write any amount of loop in these languages. It will not change. It will not affect much. But in MATLAB and Python, it creates problem. So we use vectorization techniques to avoid for loops in MATLAB and Python. All these things are programming aspects, but if you are interested, you can see this course. It will be helpful. I hope it was uh, something would have been of use to you on this discussion.
Yes, sir.
Okay, so we move forward. And yeah, we discussed this in power flow problems. We discuss all these things. Single line diagram, any network, we always want to see it represented using a single line diagram. Especially the transmission system, distribution system, we can draw single line diagram, but the difference, can you tell one difference between if I draw a single line diagram for transmission system and distribution system, will it be almost same or it can be different?
No, transmission, we need not consider this breakers, everything. We can simply represent the transmission line itself. And after all, there is a transformer. But when it
Actually,
comes to distribution, we need to
hmm,
be very specific about all these things.
even transmission also we need to consider, but once before drawing that on that single line diagram, we have to consider that. So this is done by that. Before going to this step, before drawing this single line diagram, its previous step precursor is this breaker topology processing. So in substation, there are different
Yes.
this organization of these buses. There are several topologies for the bus organization, bus configuration. There can be in distribution system like we have ring mains, and in substations we have breaker and half, double breaker, single breaker. All these things, different topologies are there. And depending upon the circuit breaker status in the substation, we know which buses are connected to which bus. This information is required to create this topology. So when we do state estimation also, we need to know which lines are connected. If there is a fault or some maintenance is going on, some circuit breakers might be open. In that case, the topology will be different. So before generating or creating this single line diagram, we need to know the status of the network topology, and which we get to know by this circuit breaker status. This SCADA system used to get the input from the RTUs, remote terminal units. So from there we used to get this circuit breaker status, and from that we can create the topology. Once we know the circuit breaker status, we know which line, which bus is connected to which bus, which other buses through which lines. Once that is fixed, then we can create the single line diagram. Similarly for distribution system, but there is one major difference between transmission system and distribution system, even when we draw the single line diagram. That's a very important, a very big, and that creates, that's the main difference, and that results in even that resulted in creation of or innovation of new methods for solving distribution system power flow. And that is one of the reason. But yes, distribution power flow, the system power flow is a bit different from conventional transmission power flow. The conventional Newton-Raphson method cannot be used for distribution power flow. It modified, there is some modification in Newton's method that can be used, modified Newton method, or there are other methods for distribution system specific. The distribution specific power flow methods are there. There is forward, backward sweep method is there. Then implicit Gauss method is there. One more fast direct load flow method is there. So yeah, I was asking difference between the two. Can you recall some difference now with the discussion that we had? It's a simple difference. Transmission versus distribution. In transmission system, now I will just give you one more hint. When we do fault analysis,
Sir,
or let's say I have the transmission system in steady state and I want to calculate, or let's say when we are solving these power flow equations, we are getting voltage and angle, right?
yes.
For each buses. So that voltage is for which phase?
Pardon, sir. Which phase?
Yes, we have a three-phase system, right?
Yes, sir. Yes, sir.
Which phase voltage is that? Because we are getting only one
One
voltage per
voltage.
bus,
Yes.
right? One voltage for each bus. But actually, it's a three-bus system.
Three-phase system.
Yes, sorry, three-phase system.
Yes, sir. Yes, sir.
So, which voltage is that? So the one difference, major difference between transmission and distribution is that here, when we draw single line diagram, we consider that we are doing analysis for a single phase.
Yes, sir. One line we will take basis on system is balanced.
Yes, based on the balance. That is the main
Balance.
difference. Correct.
Yes, yes.
The transmission system, we assume that it is balanced because
Yes, sir.
the more we go up higher in voltage level,
Yes.
the three phase, the load at distribution side, we have small loads. So they create minute differences because voltage level are also very small. 240 voltage, to 230 volts is there. So that will create small difference in the voltage if their unbalance is there. But that voltage, when we aggregate those loads, and as we move up, because we have transformer, we have tap changers, so they try to keep the voltage at around 1 per unit.
So system balance
So
is the difference between transmission and
yes,
distribution.
so that is the main difference. Here transmission, we have balance system. So we always
Distribution is
say
highly unbalanced.
yes. So the distribution is unbalanced, and we cannot assume that it is balanced. We have to change these things. Therefore, the power flow the solution methods also change. We have to consider the entire three-phase unbalanced system. It is not that in transmission we cannot do that. We can do that in transmission system also. We can model the entire transmission system in its full three-phase glory. That is also possible, and that is also done in these softwares, PSCAD or these.
But how do we represent this unbalance in a single line, particularly with reference to the distribution?
So that actually it is borrowed. That concept is borrowed from transmission only. Initially, it was done for transmission system. Entire three-phase representation of transmission line, transformers, and everything. Same thing we can do for distribution also. These all the transformer connections, whether star delta, delta delta, star or delta star delta, even zigzag, all these connection we can model using matrices. So this itself is another course, distribution system analysis. If you want, you can read. This book is there. Cat's Crusting. It's the most famous book because he has done this he has pioneered this field of distribution system analysis, load power flow, distribution system power flow. Even uh, there is one software called OpenDSS. This is Open Distribution System Simulator. So they have used this book for creating that software, developing that software, entire three-phase unbalanced system with distribution with these transformer connection and circuit breakers, even switches, capacitor banks, everything we can model. Everything can be done. So that's the main difference here. We have to consider the unbalance also because this is here at transmission level always it is a three phase, or let's say always three phases will be there always. It is not there between two buses there is only one phase, and between this and this bus there are two phases or three phases. This will never happen in transmission system, but in distribution system this can happen. If you have source bus here, then there are these different feeders are there, then laterals are there. In laterals it is possible. This is a single phase load, then this can be a three phase load. Similarly here, so all these things are possible in distribution system. That's why it is little bit different. Its analysis is little different. So that we have to model. The main thing is breaker topology processing. Using this is a very important tool. The circuit breaker status, it is updated in the control center, and we are able to see the entire picture of the power system because of this information. That single line diagram which is on the screen is because of this processing first. This is the main input. Then this is the bus branch model. Here we are saying this is, we are talking about transmission system. So this is single. We are saying it is, we are only showing one line, but actually these are three phases. And when we get this voltage one angle delta, then this is for phase A. Other two phases we know that 120 degree apart. They are only, magnitude will be same, only difference is angle, because it is balanced. But in distribution system we cannot directly do that, because each phase load is different. So angles will be different. We cannot apply the same thing. We have to do the full three-phase system analysis. Then we discuss is power flow applications. These are the two broad classification: dispatch power flow and planning power flow. In planning, we use these power flow equations. The equations which we have for DC power flow, we have, sorry, P is equals to B into delta. So this is one equation for the, this is power balance equation. This is the equality constraint. Then we have inequality constraint. We know that one is this P should be between minimum and maximum. Then we have limit on flow also. Flow should be between maximum and minimum. So it is minus F and plus F. Then flow is also equals to B, let's say, this is flow and this is in between these two limits. So these are the power flow equations. And we use this equation in the optimization problem. So planning is itself an optimization problem, where the objective function can be, generally it is minimizing the cost, how to minimize the cost of new transmission lines and new generation sites. All things are fine. We want to minimize the cost subject to these constraints. So we have network. Network is there. So on each node, this is nodal balance, nodal power balance. We are considering the entire network, and we have the information of network. We have existing generators. Network information is their generation, existing generation, and their location, their capacity is known. We have existing lines, existing transmission lines, and their capacity is known. Existing load, that is also known. Their location is also known. Their profile is also known. Right now, the economic dispatch we have, economic dispatch is for the simplest version of economic dispatch which we have studied is for only one particular time instant. Right? But when we are doing this planning problem, then we have to consider 1 year horizon, or at least let's say the minimum is 1 day. 1 day we have 96 time blocks.
15 minutes each.
Yes, 15 minutes each. So if we want to solve this economic dispatch, then it will be called dynamic economic dispatch. In that case, these time 1 to T96, these are interrelated. These are dependent on each other, because this P, we will see in unit commitment. Right now we have because we have not seen that. But simplest one thing I will just add here. In economic dispatch, we're not talking about unit commitment, but even if we take the simplest case, then one important concern or constraint is that the generation, the thermal generator, gas generator, they have a ramping capability. That how much they can increase or decrease their generation in next 15 minutes. There is a limit on that. Let's say this is the existing generation and this is the, so this is t plus 1 next time block. And let's say we are talking about ramp down. The generator is trying to reduce the output. That means this difference is positive, right? Right now, let's say it is 50 and it wants to go to 30. So this will be 50 minus 30. And it should be less than, let's say, 25. And this should be greater than minus 25. So if it is 30 and 30, 50 and 30, the difference is 20. And 20 is less than 25, which is the limit. This constant is satisfied. But however, if it is 30, sorry, this is only 15, then this constant will be violated, and that's why this generator will not be allowed to reduce its input by 20. It will be only limited to 15, or it will remain at 50. So these constants will increase. So these are the these things, these equations we have studied for simple economic dispatch. But for a bigger planning, it's a part of a big planning problem. It is time coupled. Year, if you talk about next 30 years, I want to plan for next 10 years. Then I have to do 10 years planning. Then it's a time coupled problem. It's a very big problem, and these equations are a small part of it. And there can be other equipments also. Storage, energy storage can be there. Then we need to model their constraints. There are other effects devices and other devices can be there. Electric vehicle can be there. Their constraints we need to model. So all these things, different equipments can be there. So the equations which we are studying, these are only a small part of that. And that's why this planning power flow will include these power flow equations. So these equations are just a subset of that entire, that bigger problem. Similarly, the dispatch power flow. The dispatch power flow here, we are talking about, so here planning problem, we want to know how many generators we need to install, where we need to install them, how many transmission lines are needed, and where, what's their location, between which two buses, how many lines are needed. All these things we can know by doing this kind of study. And this is done frequently on an yearly basis. Then this dispatch power flow is also done on a daily basis. This is done on daily basis. Even for a 3-day basis, we do this unit commitment 3 day ahead. All these things are done. Dispatch is done every day to see loading of transmission lines, even for contingency analysis. What happens if one of the transmission line or the biggest generator it goes out? What will happen? How the power flow on the different transmission lines will change? Everything, will it lead to any overloading of transmission line? If it happens, then we need to take precautionary measures for that. So this kind of study requires these uh, power flow equations. These are different applications. Then we saw intelligence theorem. All these power flow equation is based upon this conservation of energy. If power is, this generator is injecting some power at this bus, then it is going through these two transmission line and do this load. So let's say this is P1, this is Sij, or Pij, I will say only real power if we talk. And this is Di, and this is Pik. Then P1 will be equals to, how are we going to write this? P1? Can you tell? Not P1, this is PI. Yes, PI plus.
PI, PI is equal to PIJ plus PIK.
Okay. Is this correct? Anything missing in this equation? Hmm. We have drawn four arrows here. So we need to consider all of them. Whatever is going
Yeah,
should come. The
yes,
summation
yes.
of, so what
PIJ,
is
uh,
what is missing here?
DI load is also there.
Yes, correct. So whatever generator is producing, it is
Yes,
going. First of all, the load is met,
yes, yes.
and the remaining is going to through over these
Generation,
lines.
yes, generation minus demand is the amount that is injected into the lines.
Correct. So
You
this
just
is this is correct. Similarly, we can write it for the reactive power also. So Qi minus, let's say this is Qd. Let's say d Qi, and it will be Qij plus Qik. So this is the intelligence theorem. Conservation of energy. Same thing is written here. Real and reactive power.
yes.
Then we saw that DC power flow. These are the power flow applications we have already discussed. And next was this AC power flow. In AC power flow, we have different methods starting from this Gauss saddle. This is the simplest, but the problem with Gauss saddle is, what's the problem?
Convergence. Convergence is the main problem, and then
Correct.
it takes a lot of iterations.
Hmm. So convergence issue is there. It is highly sensitive
The
to,
starting vector, starting values.
correct. First is the starting point. It is so number of iterations are more required. Number of iterations required are more. Then convergence issue, the problem is sensitivity to initial guess.
Initial guess.
And also we have seen the Gauss Seidel formulation in a particular way, but actually that way it is able to converge, but there one equation can be formulated in different way. Means Gauss Seidel formulation can be written for the same equation in different ways, but those different ways may not always converge. The way which we use for writing power flow equation, that converges, but problem is number of iterations. Gauss Seidel takes a lot of iterations. So that's the problem. For a big, its convergence is also slow. So we have different types of convergence rates. If let's say we have iterations here, and this is the error. Let's say in first iteration the error was 10 raised to power. Let's say error was 1. Okay. In second iteration the error became 10 raised to power minus 1. In third it became 10 raised to power minus 2. Fourth it became 10 raised to power minus 3. Fifth it became 10 raised to power minus 4. This is a linear. This we call it linear convergence. Because if we divide these two, yes, each successive, we will get 10. So what is the power of 10? If 10 is power, it is 1, then it is linear. If it is 10 is power 2, let's say in one iteration, first iteration the error was 1. Second iteration the error became 10 is power minus 2. Third iteration it becomes 10 is power minus 4. If you divide these successive, then it will be 10 is power minus 2, 10 square, right?
Yes.
So this is called quadratic convergence rate. The error is reducing in quadratic fashion. And if it is between 1 to 2, 1.1, 1.2 or 1.5, anything between 1 and 2, it is called sublinear. Then if it is 10 to the power 3, it is cubic, but generally we don't have any algorithm for cubic that gives us cubic convergence rate. But we have algorithms which gives us quadratic convergence rate, and Newton-Raphson is one of them.
Yes.
That is why Newton-Raphson convergence is very fast as compared to Gauss-Seidel. Gauss-Seidel is not, it does not give us quadratic convergence rate. That is the issue with Gauss-Seidel. It will give us a linear convergence rate. Then next was this, yes, to improve this, to solve this problem number of iteration, we move to Newton-Raphson. In Newton-Raphson, we do the, if we do the Taylor series expansion, then we will get this Jacobian inverse. And an update will be Jacobian inverse into this mismatch vector. This is, let's say I call it x, okay, let delta p, let's say some delta known, it's okay, delta v. This is known, this is mismatch vector. And this is our update vector. The next value of x, k plus 1 will be x plus delta x. This is update vector, and this update vector we find out using this Jacobian. And Newton-Raphson, because it gives us quadratic convergence rate, the number of iterations are
Much less compared
less
to
here, but there is one problem.
the storage requirement is high, and then it is complex to calculate the Jacobian every time, and then the mismatch vector every time. That's the main.
Yes, so that is correct. Storage requirement, computation. So per time for each iteration is more. All the number of iteration is less, but that is more, and that is because of this Jacobian.
Yes.
That takes time because there are so many terms we have to, although we have expressions for them, but it takes time. That is the only problem with, so that is why we want to do something to speed this process up. Then we go to this first quasi-Newton. This is also called the dishonest, which has been used in this lecture, this course. Dishonest Newton. This quasi-Newton is a bigger subset. This is one of the ways. One of the ways in quasi-Newton is this dishonest. That is to keep the Jacobian constant for, let us calculate the Jacobian for first iteration, and keep it for same for 3 iteration, let's say. And then again modify it and keep it same for next 2 iterations. In this way we can save some computation, we will speed it up a little bit.
Is it depend upon any factors, or how many iterations it should be taken constant?
Can you repeat?
this Jacobian that you calculate for the first time,
Yes, yes.
how do you know that I have to keep it for the constant for the next two iterations, three iterations?
Yeah, that we need to see how much that can be known, means that we can analyze by seeing the convergence, that error vector. We can keep a track of error vector. If error vector is not reducing much, that means we need to update the Jacobian.
Okay.
There is a, we need to have a balance here between the two things. One is if we do not update it for a, if we keep it constant for a more number of iteration, then it will
It
take
will take more iterations.
more time. Yes, more iteration.
Okay. So,
But if we update it in every iteration, then it takes more time. So there is a trade-off between computation time versus the number of iterations. So that, so in that case, we can see how the error vector is evolving. Based upon that, we can know for how many iteration we should keep this constant. There are other methods also. There is one method for search direction. We can improve the search direction every iteration. So that also speeds up. So that is another way. We will not go into that. These are quasi-Newton. They will do something, slight modifications in Newton. Then after that, we come to what you had said, decoupled. Then after decoupled, we can further make it fast decoupled. Only thing, although it is fast, but it will give us approximate result. The most accurate will get in NR, then in decoupled, and then in fast decoupled. This is more approximate version. But sometimes when we need quick results, we can use fast decoupled in that case, where we are not worried about the exactness, but although approximate, we can have some, yes, little bit error is permissible. There we can use fast decoupled. Here we can see these are the equation, right? This is the VI conjugate. We take the conjugate both sides, then it becomes P star IK. And I, we know I is the summation of this because on, we are talking about we have different lines. And this is for each bus we are talking. Injection at each bus. And this injection is going into this different lines. That's why it is J is equals to 1 to, this should be, here it is N is here, it should be number of lines which are connected to that bus. A better way to write is, this is the J belongs to a set omega N, or omega K, I should write K. So it is a set of lines which are connected between bus K and J. And J varies from 1 to number of lines at that node. So this N is number of line at that node. Okay. Even if we take it N, then those lines where it is not connected, voltage is not there, it will be 0. So this is divide, then we can get real and reactive power. This is one of the ways we can write it in rectangular coordinate also. So In that case, we will convert this voltages also into A plus JB form. And this is a polar form, polar representation. In rectangular coordinate, we'll be having a real and imaginary part also. A plus JB. This will be real part of voltage, and this will be imaginary part. These two terms will come. In polar coordinate, we have magnitude and angle, but in rectangular coordinate, we'll be having real and imaginary parts. This we have already talked that Jacobian const keep the Jacobian constant for few iterations. And decoupled, in decouple we will decouple for transmission system. We know that P is directly related to which quantity?
P depends upon angle.
Yes, because power is we it is directly related to the frequency of the system, and angle is directly related to the frequency part.
Frequency.
And Q is directly dependent on voltage.
Voltage.
Sorry. So this Q is uh, dependent voltage. This fact we are using, and in Jacobian term, in Jacobian matrix, we are making these two. Here we have delta and V, and this will be delta P by delta, delta Q by delta V. So these two sub matrices are zero, and we have to calculate only these two matrices. Here we were calculating four sub matrices. Here we need to calculate only two sub matrices. This will sure increase, it will reduce the time per iteration. Also, in we make these two assumptions also, that angle, here we don't make any assumption on angle or R and X. But here we make assumption that angle difference is less, so we can approximate sine theta by theta and cos theta by 1. And also we know that this X by R ratio is very high, 2 to 10. We can neglect this R values, resistance. So G term, this in this here, this G terms, they will vanish. There is, this is another, yes, you were saying?
For fast decoupled load flow, I think these are the assumptions.
These are assumptions for decoupled, and fast decoupled will make two more assumptions. On top of these, we will make two more assumptions. One is that voltage. We know that voltage is nearly 1 per unit.
Yes.
Yes, and another one more is that this Q1 is less than Vn and Vn square. This will neglect that shunt part. This will make further, this will make the Jacobian itself constant, because it will simply depend upon that B prime and B double prime, which we can calculate directly from these Y matrix, Y bus matrix. And because these are constant and their inverse is a very computationally intensive operation. We never do this. We say the inverse of A is adjoint of A divided by determinant of A. Determinant is a iterative. It's a recursion. It's a recursive operation. So this calculating A inverse for a very large system is, it takes time. It's an iterative process. We never use this way. That's why we use different methods. Do you know? How do we calculate inverse without using inverse formula? Means you would have heard this or even studied Gauss elimination.
Gas elimination. Yes, yes.
Yeah.
Matrix
So
operation.
this is the simplest Gauss
Yeah.
elimination, but it takes it is not that good. Then next is LU decomposition.
Mm.
We have different decomposition techniques which we use. Once, because this Jacobian is constant, we can just calculate LU, its LU factors only once.
Yes, at the
Then
beginning.
every time we can use these LU factors to calculate the inverse. So it reduces the computation significantly. There is another QR decomposition. QR is even a good decomposition, but it uh, it takes more time than this LU. Then singular value decomposition are also there. So this is increasing complexity. So LU is widely used here. LU we can use. Once we have to do the LU decomposition before starting, and every time we can use this LU. Let's say I want to write no, AX is equals to B, and I want to calculate X. Then I have made these LU factors. LU X is equals to B. In ux I can write as y. So ux is equals to y. Ly is equals to b. This is a lower triangular matrix. We can directly calculate y by forward substitution. And here u is upper triangular matrix, and we can calculate, because y is known from here, we can calculate x using backward substitution. So once LU factors are known, we can easily calculate x inverse. Because our Ax is equals to B. We need not do the inverse, implicit inverse, explicit inverse. Implicitly it is done. Here our objective is to calculate x, which is A inverse B. But without doing inverse, we are able to calculate that. So that's why these decomposition techniques are used, especially for large matrices. And our network is, it's very large. We have 10,000 buses, even more than that. Matrix will be this A matrix, B matrix, or Jacobian matrix will be 10,000 cos 10,000. It's a very huge matrix. And how many entries are there? 10 to the power 8 entries are there. It is a very huge matrix. And most of them are zero.
Zeros. Yes.
And most of them are zero. So why to store them? Then another thing, this is the first thing. Another thing which comes up is, why do we store zero? When most of them are zero, no need to store them. Then we go to sparse matrices. We use sparse matrix computation. Sparse representation of these matrices. And then we use, first we convert the matrix into sparse matrix, and then we do LU decomposition. The LU decomposition is done using, it can be done using Gauss elimination also, and there are other methods also. Then use forward backward substitution to calculate this X, or the update vector. So in all the software, these matrices are converted into sparse matrix. Then LU decomposition is done whenever inverse is required. LU or QR. Okay, is this clear?
Yes, sir.
I hope this all these things are helping. These are useful for you. Because
Sir.
in one book we don't find all these things.
Yes, sir.
Very difficult.
So regarding this decoupled load flow,
Yes.
though we are reducing the calculation is there any no from the time point of view? Is there any advantage from Newton-Raphson to decoupled load flow?
Yes, yes, time will certainly reduce because first of all, we are making these assumptions, so these expressions are becoming simpler. Then another thing, these we are only calculating two submatrices. If you compare
Okay.
these two, the time is reduced by
But
around
it takes
one
a
by
number
eight.
of iterations, maybe more compared to the original Newton-Raphson method, because you're assuming these
Yes,
two
correct. So
power.
time per iteration,
Time per iteration reduces definitely, but
then
overall time
we
for
we need
convergence.
to compare these time per iteration versus number of iteration.
I'm talking about time per iteration into number of iterations.
Yes, yes. So that we need to compare.
I think there may not be much advantage because it
And
takes more
actually,
number of iterations.
when we don't see that advantage because when we see any example in generally in books, then we talk about small 10 bus system or even 4 bus system, 5 bus system. You won't see,
Complexity reduces definitely.
you don't see the difference. But if you go to a very large system, then we can easily see that difference. Even one simplification in the expression results in the reduction in time is very much. It's too. I think I had that. I don't remember whether it's decoupled or fast decoupled, but the time required it becomes around 1/8 of in compared to Newton Raphson. So time per iteration certainly it reduces a lot.
Yeah, iteration definitely.
And number
But
of iteration will not increase that proportion. If you multiply this time per iteration into number of iteration, the reduction in this time per iteration is much more in comparison to the number of iteration, increase in number
number
of
of iterations.
iteration. That's why overall it is helping us.
Okay.
If we compare the number of iteration in Newton-Raphson and decouple, the number of iteration will not be it will not be like twice. If
Okay.
Newton-Raphson was taking 5, then it will take 10. It will not be there. It will be less than that. But the number of that time taken will be certainly more than the order of that will be more than 2.
Okay.
Certainly. So that is why sorry, it is beneficial.
Okay.
Okay. Yeah, I had one. Here I will tell that. This was the main the assumption which we are making here that X by R ratio is high. So I was before in previous slides also I was taking the difference between talking about difference between transmission and distribution, and this is also one another major difference.
Yeah.
In distribution we have high R by X ratio or
Always.
low X by R ratio.
Hmm.
So we cannot neglect this. We cannot use fast decoupled or decoupled in distribution
Yeah.
system.
Yeah.
We have to use Newton, and that too if we use the same Newton which we are using here, then it has poor convergence for distribution system because of this R by X. That's why we need to modify them or use different methods, and those methods are very simple. Forward backward sweep is a very simple method, and it converges very fast also within 2, 3, 4 iterations for a small system.
Yes.
And even time per iteration also very small for in comparison to Newton, because Newton we have to do inverse also, these sine cosine terms, these complicated computations we need to do in that. But for that distribution system, it is little, it's not that complex. Okay, so Yeah, now we are moving to the DC part. For DC, we are assuming these things. We already have this. Actually, the DC power flow, you can say it is coming from that fast decoupled only. Where we stopped in fast decouple, from there we can go to DC power flow.
So why it is called DC power flow? Because we are
Actually,
calculating real power as well as reactive power.
no, in this DC power flow, there is no real reactive power. Right? We assume that reactive power is not there. It is zero. We are only calculating the active power in.
You are considering angles and everything.
Yeah, angle is there. Voltage we are, because we are assuming it is one, right? So reactive power, because there is the voltage difference between the two buses, and we know that the reactive power is proportional to the difference between the voltages, V1
Voltages.
and V2. And we are assuming that voltage are 1 per unit, so Q becomes
No
0.
reactive power.
No reactive power.
No reactive
Only
power.
P, we see
But
only power,
yes,
active power and angles, reactive power.
angles you are considering. So
Yes.
why still it
Yeah.
is called as DC power flow?
Because it is like this. If the power flow, we we say this is sine, or if we make that
Angular difference.
approximation, it is
Proportional to angular
simply,
difference.
yeah, simply angle difference divided by
Difference.
x, right?
Yeah.
So this is x. If we take a DC circuit, let's say this is a DC circuit, and the resistance is R, and I want to find out current. So what will be current here? Simply V1
V1
minus
minus V2
V2
by
by
R.
R. Right? And this resembles this DC circuit analogy. That's why they have DC power flow. Otherwise, there is no
Yeah.
any such logic behind that. This is the only someone started this kind of, someone related this DC network current, calculation of current in a DC network. He said that these two formulas, they look similar. Same, V1 minus V2 by R, here theta 1 minus theta 2 by X. Form is same, but they are actually different quantities. That is the only uh, the same. There is no other logic behind that. Why it's called DC power?
Yeah. But considering the existing system, now
Yeah.
which is now reactive power is requirement is very high. Uh, how can we neglect this reactive power in the present system?
DC power flow, it depends upon the application where we are using. You will see DC power flow application. Where do you find DC power flow application? DC power flow is a one step solution. It gives us one step solution. Whatever method we have seen, Gauss Seidel, Newton Raphson, decoupled or fast decoupled, all these are iterative solution. At least more than one iterations are required to solve this problem, but DC power flow will give you one step solution. No iteration is required, single step solution. When we require very fast solution, when a system is very large, even one step time to do one step, one iteration is also quite large. Let's say we have to take decision for each 15 minutes, right? For each 15 minutes, we have to dispatch the generator. So we need to do market clearing. There is a real time market. You know, we have
Yeah,
day ahead market and real time market.
the market.
Just a minute. Yeah. In real time market, it's a 15-minute time block. For each 15-minute block, the generator needs to be, each generator needs to be told that you have to generate this much. Suppose a generator was generating 100 megawatt. Then next after 15 minutes, we have to, the generator need to generate 120 minutes. The generator has to be given that information beforehand, at least 5 minutes before that. So for that, and for there are several generators and demand distribution companies or another entities, commercial consumers can be there. They together, they are going to power exchange to buy electricity. Energy, they are buying energy for each time block they are buying. If they are short of energy, or they can even sell if they have access. So which generator will generate how much? Which company is going, distribution company or consumer is going to get how much electricity? That is known after solving a problem. It is called bid matching. Generators, they will, the distribution company, they bid that I am ready to give rupees 10 for each unit, for each unit. Some distribution company will bid rupees 20 for each unit I am ready to give for 100 megawatt or 200 megawatts. So generator will also do that. Finally, the solution comes out and each generator is told that you have to generate this much. But that solution has to be very quick because next 15 minutes everything has to change. That solution has to change to be calculated very quick. And after that solution is calculated, the network operator, which is POSOCO or grid controller of India now, the grid controller of India has to check, is that schedule feasible? Can my network handle that? All this thing has to happen within 15 minutes. There are so many things that happen within 15-minute time block. Earlier it was 30 minutes because we are not able to do it in 15 minutes at that time. But because of now better solvers, we are able to do that in 15 minutes itself. So, so 15 minutes is the entire time block, but we have to do it within minute. I have within 1 minute, I want to know how much each generator should do, should generate, what will be the line flow, everything I want to know in 1 minute. And there are so many generators. So it has to be very quick. In that case, the bid matching uses this DC power flow. Because the network operator is always having, he always keeps an eye on the network. He always has a margin on the power flow. So whatever power flow are coming out of this, whatever generation schedule are coming out of the bid matching algorithm, that the operator will try to run its own power flow and try to match it. And because there are certain margins also, and he can handle things. Whenever a quick solution is required, we are using power flow. So right now in market, power exchanges, DC power flow equations are used. This is one application. Another application where DC power flow is used in planning problems. Let's say I want to plan for next 30 years. So Central Electricity Authority, they plan for next 30 years. So they have given this 2030 or even next 10 years, they have given this 2030 transmission expansion plan that we need to erect these new transmission lines, storage has to be procured and all these things. Because in 1 year, we have 365 days and 24 hours. So it is 8760 hours. And this is into 10. If you are doing it for 10 years, then you have 87600 hours. And these hours are time linked because of ramping constraint and other constraints. This is, these are, these number of hours, for each hours you have several constraints. Each constraint for transmission line, for generators, for HVDC lines, for FEC devices, so many constraints. Then the problem size becomes these constraints can be more than 1,000 constraints. For each bus, there will be one power balance equation, nodal power balance. If 10,000 buses are there, 10,000 nodal power balance constraint. If 10,000 generators are there, 10,000 into 87600 constraints are there. So you can see how many, what is the problem size here? The billions of variables and constraints are there. Solvers cannot handle this much. We don't have solvers. Problem become intractable. In that case, to further, if you use AC power flow, then those equations are non-linear. Non-linear solvers with such a big problem size we cannot solve. For that, either we do approximation or we do relaxation. AC power flow, one is approximation. Approximation is this DC power flow. DC power flow is an approximation. Then we have relaxation. We relax certain constraints. Wherever we get this product of voltage. In power flow, we have this product, right? These are the product terms. These are non-linear terms. We relax these terms. And we get different relaxations, second order cone programming, semi-definite programming. These are relaxed versions of same AC power flow. This is very fast. And these also now several solvers can solve these SOCP and SDP problems also. Till when the time horizon is very large, very huge, to get tractable formulations, we use DC power flow. So this is another example where we use DC power flow. Because as that is 30 years ahead, we have room for changes, updates to that. For the next 30 years, we are just getting an idea. We are trying to get an idea that how much transmission, how many transmission lines or how many new generators are required. Next, after 5 years, I can do another. For next 5 years, I can do a detailed analysis to do that. Right? For 30 years, we can, because budgetary requirements are there. If there is a rough idea, it is not that rough also, it is approximation, but it will be close to the actual answer. We get a rough idea, a fair idea that this much investment would be required. Then the government and the agencies can plan in that way. Yes, we don't have that much budget, so we reduce some. We'll have only one or two generators. For next 5 years, they can plan. How to plan those 30 years also we need to see. Next 5 years, I will do this. After that, I can change. I can revise this. I can use the relaxed versions, whereas AC power flow for 1 year. Because generators, construction of a coal generator requires several years, 5, 6, 7 years. At least for 10 years planning horizon, I need to plan before 10 years itself. 10 years is also a very big framework. Then another thing many things can be done. If you want to use AC power flow also, then instead of using 8760, this also is reduced. We take certain scenarios for representative days, representative hours, representative seasons. So many things can be done to reduce the problem size. But the overall, the gist or crux is that whenever we want to reduce the problem size, we want quick solutions, DC power flow is preferred. I hope that's clear.
Yes.
Okay. The next assumption that we make is this expire ratio. We are same. These are same approximation which we are using for fast decoupled also.
All the couple.
Same equation. So the DC power flow comes from that fast decoupled only.
Yes.
Only the difference here is we are having only a single shot solution, one step solution. That's the only difference from decoupled power flow. And here we are not have we don't have reactive power. We are not even considering reactive power. That is another difference. So like this. We'll take one example. I think we need to move fast. Half an hour. We'll take one example for DC power flow. There I will explain that how to calculate that B matrix. The next thing was the transmission calculation of transmission losses. Here, it can be done in using historical data because we have the historical data of what flows were in last 1 year. We can average out and calculate how much was the loss in 1 year. We can. So, do you have any idea how much? What is the percentage transmission loss in India on an average?
Transmission loss, I think it is around 16 to 20%, sir.
That is entire eight aggregate transmission commercial loss. That is around 16%. But transmission, if we talk only about transmission loss, then that is around. It depends on the region also, but maximum up to 4%, to 3 to 4%. In some regions, it is 2.5% also. We have 5 regions, right? So not more than 4%. But then distribution losses are they are more. Even the theft and everything is concerned in that when we calculate ATC. Uh, Aggregate technical and commercial losses, those are in that case theft is also considered in distribution system. We see theft is common, especially in rural areas. So that is also taken into account. That's why that figure is very large, 16%. Then that first is that historical data, then we can use that same NR power flow algorithms also. And last one is the loss formula. Then for that only this derivation and example was discussed. This was the motivation why here we need to calculate these losses. If we have same generator connected, one is connected to this bus 2 and another is connected to bus 1, and this is connected to bus 2 via a transmission line. Both are identical generator. They want to meet a 500 megawatt load. Right? Because both are identical. And let's say if we load both of them by 250 megawatts, both of them are generating 250 megawatts. Then because of this loss, there is a 0.002 multiplied by 250 square. This will give you 12.5 megawatt. There will be a loss of 12.5 megawatt. Although we want to meet a 500 megawatt, we are not able to meet. We are only able to meet 487.5. 12.5 megawatt is getting lost in the transmission line. So our question is we want to know which generator should cater to that loss. Because loss also, that's why the generation will always be more than demand. Plus, the loss has to be taken care by generator itself. So that one generator can take into that can be taken care by one generator or more than one generator. That bus we call it slack bus, right? Slack bus. It does two purposes. One is it provides a reference for angle theta. Then it takes care of losses. This slack can be one bus or it can be a distributed. In that case, so generally it is we have a confusion. We say that slack bus and reference bus are same. But these two concepts are different. A reference bus is required. One bus has to be a reference bus. But a slack bus can be a one bus also. The same bus can be slack bus also. It cannot be. And the slack bus can be one bus or it can be many. In if many buses are if all the buses are involved in slack bus, then we use that participation factor. If one unit change in load, increase or decrease, how that is being shared by all the generators that we have seen right in participation factor in previous week. That Pi new is equals to Pi old plus that alpha times the change in power. This participation factor. The change is distributed among all the generators. So that is concept of that distributed slack. So reference bus is different and slack can be reference or cannot. That is an important idea. Here we want to know that which generator. So if we see the minimum cost solution, for that you have to write the Lagrange multiplier, and finally we will get this. One is this power balance equation. Load demand plus loss is equals to total generation. And then this is one equation, and then we have these two equations. So together these are called coordination equation. We need to solve them. Right here, this is because this will be a quadratic. You will get a cubic equation here. Substitute for P2 here. From this equation, substitute P2 in this equation. So you need to write P2 is equals to 500 plus 0.0002 P1 square minus P1. Substitute this in this equation. Then you will get a cubic equation and solve it. Finally, you will get your solution as this 178.88 and 327.52. This will be minimum solution, minimum cost solution. And it will be able to meet the demand, and the loss comes out to be 6.4. Okay. In first case also, the cost, this is the minimum cost solution. Next is if generator 1 supplies all the losses. So this will be kept at 250, and you write this is 250. And from here directly P1 can be calculated. It is a quadratic equation. So this will become 250 plus 0.0002 P1 square minus P1 is equals to 0. It's a quadratic equation. You solve it, you will get this P1 value. And if you substitute that here in this loss, that loss will be 0.0002 into 263.93 square. Then you will get this loss, 13.93. So in this case, loss is more. So if we compare these two, that means it is saying that you generate more. The losses should be catered by the generator which is near to the
Closer to the load.
Closer to the load. Correct. And the last one is this minimum loss. If you want to get minimum loss, then we need to generate more from this. But in that case, cost can be more. Cost is higher than minimum solution. Here I can compare the minimum cost solution. This is minimum loss solution. So here loss is 6.4. Here loss is minimum, but cost here is minimum. So this is a multi-objective problem. These are the two conflicting objectives. When we want to reduce cost, loss is increasing. If you want the vice versa. So multi-objective we can do if we plot here cost versus loss. Then we will get something like this. And this is called a Pareto front. These are infeasible solutions. Above here you will get feasible solutions, but you will not be able to. But these solutions are the best one. Now where what is the requirement? We can base upon that. For a particular loss, we can know the cost. Okay. So this is for multi-objective system optimization. Okay. Then we did this B matrix loss formula. It is dependent upon the generation, all the generation. All this is vector of size. This is n cross 1, B is n cross n, and this is 1 cross n. So finally, we'll get a one term, one scalar value. There is some, this should be P here. This is a vector. This is a vector. This is 1 cross n. This is n cross n. Single value. This is also a scalar. So we will get a scalar loss value. Similarly, this we can write. This is written in matrix form, and this is written in summation form. And same thing, if we do Lagrange multiplier, we find that this is here. The problem here is this is a coupled problem. This lambda is a variable, right? We don't know lambda. And P is also a variable. We don't know P, and we are getting a product of these two terms. It's a non-linear. The coordination equation here is non-linear equation. Now we have non-linear solvers available. We can do that. Earlier we didn't have, so we use that iterative solution, consider one of them constant and try to find out the best lambda. Then again, change the penalty factor, adjust our lambda such that the difference between two successive iteration is less. We keep on doing that till we converge. Iterate that difference is almost close to zero or whatever tolerance we have set. And this was the reference bus penalty factor. This also we can calculate. The loss calculation, the loss formula that assumes that reference bus, whatever changes are happening, it is compensated by the reference bus. Same thing we will also see in the, I think next week or next week, we will see this power transfer, distribution factors or injection shift factors. We will see all these things. There it will be more clear. And this is one example. This is the same example which was there in the slide. Were you able to understand that example?
Yes, sir.
Okay, it is simple. It is using that only thing is that superposition principle.
Yeah.
We can calculate those current distribution factor by using superposition. Once in one case, we at a time we consider only one generator. We consider first we can say only G1, then we can say only G2 and calculate these current factors. And B1, B2, B11, B12, B22 we can calculate. So let us take questions now. Some simple questions. And I will, last question is that DC power flow. We will solve that question. That is a good, and still how to, there is a doubt or confusion between the B matrix which we use for fast decoupled and B matrix which we use for DC power flow. Those two are not same. Those two are different.
Yeah.
That is very important. And that slight difference of minus sign is there.
Yeah. Minus.
That is very important. We cannot use Y bus. It is minus of Y bus. That we will see through one example. Let us start with this. Which diagram represent the graphical representation of a power system showing the interconnection of buses, transmission line, and generating unit? Yeah, it's a very simple question. It's one line diagram. So this one line diagram, which we have already discussed, we get this by using this information, right? And this information is this given by this topology processor, topology processor. We call it network topology analyzer or processor. In state estimation is one of the essential part of any control system. Any SCADA or control system which we have in NLDCs, RLDCs, state estimation is the backbone of it. And that state estimation is the first step is this topology estimation. It's a very important step tool. What does Newton-Raphson method applied to power flow equations aim to determine? So,
The magnitudes and angles.
yeah, so once we know the voltage magnitude angles, everything else we can easily calculate. We can calculate currents, and when currents are known, we can calculate power flows also, losses, everything is we can calculate. What is the main purpose of Gauss-Seidel method in power flow analysis?
Uh, I think yeah, model
Yeah.
voltage dependent loads and power system.
Yes, in Gauss-Seidel method we can do that. We can model voltage dependent load.
Voltage dependent loads.
Correct. Next is what does term decoupled power flow refer
Separate
to?
real and reactive power calculations.
Which
Technique to
option?
separate
Method.
voltage. See,
Yeah, correct. Technique
then
to separate voltage and angle calculation power system. Yes.
power flows.
That is the decoupling here. So we are decoupling P and,
Yeah.
Q and
Okay.
V. But in distribution system, we cannot do that. So there P is dependent on both theta and V, and Q is also dependent on both theta and V. And yeah, this. How is economic dispatch problem with penalty factors different from one without penalty factors? It considers economic cost of power losses, includes additional constraint for environmental regulation. This is not at all correct. Optimization power flow considering voltage dependent loads, no. Account for coordination equation power system equation operation.
Considers the economic cost of power losses.
Yes, this is correct.
Because coordination equation is there in ED without losses and with losses.
Yes.
Coordination equation, exact coordination equation, that is what we call with penalty factor.
Hmm.
So D is not a correct option. Yeah.
He is correct. Yeah, that reference bus penalty factor.
Penalty factor.
What does it refers to? Impose on generating units for violating operation limit? No.
Adjustment factors applied to generator costs in the
Yeah, this is
economic
correct.
dispatching.
Correct, correct. This is correct. What is the purpose of which one?
Incidence matrix and power system analysis. Incidence matrix, topology, connectivity of topology.
Uh, Connectivity and topology of power systems. This
Connectivity.
incidence matrix is it's a very generic term used in graph theory.
Yeah.
And graph theory, we have that same concept we have borrowed from graph theory, and even the power system network we represent in terms of graph. That node, the bus, or we also call it as node, right? That node and branch term that comes from these graph theory. These are graph
Graph theory.
theory.
Yeah.
Yes. So all these softwares that we use for MATLAB or maybe PSCAD, behind everything that graph theory concepts are used.
Yeah.
Incidence matrix, in that cut set matrix, all these things are used, right? They are
Yeah.
used. And this is the last question. Here we'll do that DC power flow. This is bus 1, 2, and 3. You have to calculate the line flows and considering a 100 MVA base.
First of all, you have to
Okay.
convert all these powers into per unit.
Yes, so that is very easy here because
Yeah, I understand.
just divide by 100. So let us first do that power flow. Write the injection at each bus. And this is 2 per unit, right? First 2 per unit. What is injection on second bus?
That is 700. 100 is the load, I think. That is one. So 6 is the injection.
Yes, 6 per unit. And what is the injection on bus 3?
This is -8.
Yeah, -8 because generation is not there, so it is 0 minus 8.
Yeah.
Correct. So this is our injection vector. Now, if we calculate the Y bus here, let's say, what will be the Y bus? Let us first write these. These are 1 per unit. These are X values.
-10 and -20.
This is minus J10,
-J10 -J20.
minus J15.
Okay.
So what will be this?
This is
This
-30
minus
-J30.
J30. Okay,
J30.
let us take this J out.
J out.
This is J30 and this will be
Plus
10
plus
plus 10.
10
Yes,
plus
plus 10.
20.
20 and
Then
this will be
after
10
that 10
and
minus 25.
25.
Then
This is
15.
2 and 3.
15.
15. Yes. Now these two are same.
20.
Symmetry. And this is 30,
This is 35. Minus
35.
35.
Correct. Yeah. So now this is Y bus. Now we will write, we know this, right? Flow, we can write it like this. Flow on a line. Considering that angles are very small. So sine theta becomes this theta. Now we will write this injection that we know that P1. P1 is equals to this flow. Let us assume the direction is 1 to 2, 1 to 3 and 2 to 3. These are the direction. So what will be this? We are using the intelligence theorem here.
P12 plus P13.
Yes, so what is P12? P12 is
P12 is
delta 1
delta 2 by
x j.1. No, sorry, no j. J is not required here. This is simply 0.1.
0.1. Yes.
And then plus delta 1
Delta
minus
1 is
delta
delta 3.
by 0.05.
0.05.
Okay, so P2 is
It is 2 3 minus 1 2.
delta 2
Delta 2 minus delta 3 by 0.0667
plus
is when you write 2 1 now, that is negative, or else delta 2 minus delta 1 by 0.1.
for actual flow. This is incoming in. Huh?
Yes. You take it negative, or else you can write delta 2 minus delta 1 by 0.1. Both are
Yes.
nothing same.
This is 0.1. And similarly, P3 will be
Delta 3 minus delta 1 0.05. Delta 3 minus delta 2 by 0.0667.
Yes. Now if we, this we can write as, this is B1, 1, 2. We can write that this is B1, 2. Completely. Can write this is 1 by x12 plus 1 by x1 3
That's what 3.
delta 1 minus 1 by x12 delta 2 minus 1 by
X13
x13 delta 3,
3.
and this will be minus x12 delta 1 plus 1 by x12 plus 1 by x23 delta 2 minus 1 by x13 delta 3, and this is minus 1 by,
X23, I think.
which one, this one, yeah, x23.
X23.
This will be x 1
X1
3
3 delta 1
x1
minus
2,
X1 X23.
yeah, plus this will be x
X1
1
3
3
plus plus 2 3.
x23 delta 3.
3.
So this is 2.
This is 2. Yeah.
So if we now, if we write, if we compare these two, if we write this, then it will be this no, 10 plus x, we can write this is 10, this is 20, this will be 30, this will be minus 10, minus 20, minus 10, 25, minus 15, minus 20,
Minus
minus
of that y.
sorry.
Yeah. Whatever y cost we got,
Yes,
simply multiply minus.
correct. So this is actually imaginary part of,
Y
if
cost.
we remove this j, this is imaginary part of y, or we call it by b also.
B
Yeah,
matrix.
so B matrix. This is B matrix, but this is minus times of B.
Minus
This
B
is the
cost.
difference, and this is very important. So we have to remember this. So this is, and this directly comes by using, not this. We'll see here. This will directly come if we use this.
Yeah.
We can see, like, let me add one page, or let me write it. E, okay. So we have B in lecture, it is D matrix, BD into A into delta. This is flow. So flow, what we write? Flow is delta 1 minus delta 2 by X, or if it is I, it is J, this is X, I, J. Okay, this is flow, right? So we can write like this is 1 by X, I, J, and this is delta I minus delta J. This is a multiplication, and this is something is happening here. The difference is taken here. Delta I minus delta J. Flow is a line L cross 1 if L lines are there. This is a, we want to multiply 1 by X to each of the element. This is a L cross L matrix, but it is a diagonal matrix. Diagonal of 1 by X ij. So in our case, it will be diagonal of 10 or 10, then 20 and 15. So it will be a matrix like this 0, 0, 0, 20, 0, 0, 0, 15. Yeah, this is a D matrix. And this A matrix is the incidence matrix. And this, it's dimension will be L cross N.
Yeah.
And so here, this is L, line 1, line 2, line 3. And here we have nodes 1, 2, 3. So line 1 is connected between 1 and 2, but it is originating from 1 and ending on 2. So it is like this. 1 to 2 directed like this. The graph is always directed. Yeah, so this is 3, 1, 2, 1, 3, and 2, 3. So 1 to 2, first line, line 1. This is line 2. This is line 3. Line 3, 2 is connected with 1 and 3. 1 minus 1. 2 is connected between 1 and minus 2 and 3. 1 minus 1. So this becomes A matrix. And then delta is n cross 1. Either we can write like this, or we can also write it like this. D, I will call it A delta. Let me call this A tilde. I can also write it like this. D will remain same, L cross L. I can write it as L cross n minus 1 and delta as n minus 1 cross 1, because we know that delta 1 is 0, reference. So I can remove that row. So in this A matrix, if I remove this first row and first column, I will be left with this matrix. And I am calling this as A matrix. So in this case, A will be D is this 0, D is same. And A matrix is this 0, 1, 0, minus 1, 1, minus 1. And then we have a delta here, delta 2 and delta 3. So this will give us flow. But now we want to calculate delta first. So delta we can calculate. We have this B into delta. Delta is n minus 1 cross 1. So B has to be L
I think
cross.
the size should be 3 by 2.
Which one?
Matrix A.
Uh,
Because D is 3 by 3.
3
A
by
is
3.
2 by 2. A is 2 by 2. So you cannot multiply now. That should be
Yes,
3 by 2.
yes. Yes, yes, correct, correct.
3
I
by
have
2
made.
means we have to consider column 2 and 3.
Yeah, sorry, I made a mistake here. What we do for B matrix, I did that. Sorry.
Yeah.
We have to remove only column, not row. So it will be 1, 0. Sorry. This is correct. Now it is correct. We have to remove only this column corresponding to node 1. Right? We are only remove because node 1 is the reference.
It should be 3 by 2. So consider
Yeah.
column 2 and column 3.
Yes, yes.
Minus 1,
This,
0, 0 minus 1.
yes, yes. Correct.
1 minus 1. Yeah.
So we have to remove only this column. Keep these two columns. Now it is 3 by 2. This is correct. Okay, so the P is B into delta. Delta is n minus 1 cross 1. So B has to be L cross n minus 1 cross n minus 1. B is n minus 1 cross. Here we have to remove the first row and first column. So if we calculate B, this B dash. In this, if we remove this first row and first column, we are left with this matrix. We have to use this matrix. The same thing is written here. This A matrix we have calculated, D matrix if we have, D we can directly calculate that like this also. It's A tilde transpose D A transpose, because this is A was L cross N, right? And this is L cross, this is transpose, so this is N cross L. D is L cross L and A is L cross N. So you will get N cross N B matrix. This is same. This matrix B prime, or we call it B tilde. Yeah. In this, from this we have to remove first column and first row. And if you want to avoid this thing, remembering of, if you want to, you don't want to remember this again and again, what you can do? Instead of this, directly take A transpose D A. Then A is this one, reduced this after removing one column. So this becomes n minus 1 cross L. This is L cross L. This is L cross n minus 1. Then you will get n minus 1 cross n minus 1. Directly you will get this B matrix. Then take inverse, multiply it by P vector. You will get this delta. Then this we already know, D into A into delta. So A matrix is this reduced by removing one column. So this is L cross n minus 1, n minus 1 cross 1, and this is L cross L. So L cross, here you can use any A matrix, either full or reduced, but correspondingly delta also has to be full or reduced. Okay. Hey, is this clear?
Yes, sir. Yes, sir.
So this is a very, here we make mistake. This minus sign in exams it happens.
Yeah,
We forget this minus sign, then everything becomes. So here you can use directly these matrices, then no need to remember that minus sign.
yeah.
Directly you will get this because it is coming from the network topology itself. Okay, any other doubts?
Sir, we are taking, say, for generation is balanced by demand and losses. So we write
Yes,
generation is equal to demand plus losses.
yes,
Uh, this is true for both real and reactive powers.
yes,
So real power generation equal to real power demand plus real power losses.
yes,
So, in that the real power, when it comes to real power, so you know that the real power losses will be dissipated in the form of heat. So some of the power is being dissipated in the form of heat. So that is why generation should be more than demand.
yes,
But when it comes to reactive power,
yes,
uh, the same equation we have reactive power generation equal to reactive power demand plus reactive power losses.
yes.
But when it comes to reactive power, the reactive
Hmm.
power is generated in one cycle and dissipated in the other cycle.
Hmm.
Generate is reactive power is positive in one cycle, negative in the off cycle. Now, where is the question of reactive power loss? Now, how this
If you
if it is reactive power loss, how this reactive power loss is being dissipated?
that loss happens in the conversion from, there is a conversion of electromagnetic to electrostatic and vice versa. This conversion happens. Here we have L and here we have C capacitance.
Yeah.
So this
If
conversion,
inductor say, let us say, absorbs reactive power, capacitor generates reactive power. So it generates in one cycle, whereas inductor absorbs in the other cycle.
yes,
So where is the question of this loss? And if at all there is a loss, how this is being dissipated?
this it is not dissipated in the form of heat, that is confirmed, but I will think and tell you again in the next class.
Yeah, yes,
Okay.
sir. So we will discuss in the next class.
It's yeah, I will surely tell you in the next. Please
Yes,
ask me this question again. I will think over it
yes, sir,
and tell you.
definitely, definitely.
Thank
Okay,
you for
okay,
the
sir.
question.
Thank
I
you, sir.
will.
Thank you.
Thank you. Thank you.
Thank you, sir.
See you. Like, oh, I just want to tell you one thing that next Tuesday I will not be able to organize this class. So to next week the class will be on Saturday.
The coming Saturday, sir.
No, next week, next set. So next week, 24th August. Next class will
Okay,
be on
okay,
August 24th. You will get a mail also, and
okay,
on
okay, sir.
the link will be shared. Time and everything will be mentioned because I am not available next
Okay,
Tuesday.
okay, sir. Okay.
Okay, so happy Independence Day, and
Thank you,
yeah.
sir. Thank you, sir.
Okay, thank you for joining.
Thank you, sir.
Okay, see you.